Sorry. Hello. Hello, good evening. I am Saurabh and I welcome all of you to this session for the NPTEL course IC Engines and Gas Turbines. This is session 6 and I think this is the last session for the IC Engines, and from the next session onwards, we will start the gas turbines. Okay. So let's start. Here is the question number 1. It says, what is the primary reason for cooling an internal combustion engine? So you know that cooling system is a very important part for any internal combustion engine. So this is asking that what is the primary purpose for this cooling system? So we have 4 options. Option A, to increase the efficiency of combustion. Option B, to prevent the lubrication system from malfunctioning. Option C, to reduce exhaust emissions. And last option, to increase the power output of the engine. So I think this is quite intuitive and you can easily answer this question. That cooling system will not affect the efficiency of the combustion. In fact, the efficiency of combustion is higher if the combustion is happening at higher temperature, right? We have discussed this in some previous session, that if the average temperature of the heat addition is higher, then efficiency is increased. So cooling will not, increase the efficiency. Technically, it can reduce the efficiency, but it will not increase the efficiency. Okay. If you are cooling too much, then efficiency can be reduced. But anyway, the cooling system is not for increasing the efficiency. Option C says to reduce the exhaust emission. So again, this is not correct, right? And to increase the power output of the engine, this is also not correct. So the only correct option is option B, to prevent the lubrication system from malfunctioning. So if you are not cooling the engine, then temperatures can reach very, very high, and at very high temperatures, your lubrication system can fail. Okay. So to prevent the lubrication system from malfunctioning, we are using cooling. Okay. Cooling, we are cooling the engine. Okay. So there are various type of, cooling systems: water cooled, air cooled. Okay. So the correct answer for this question is option B. Okay. So moving to the next question. Question number 2, it says, which of the following is a disadvantage of using air as a coolant in an internal combustion engine? So as we just discussed that we use some coolant for cooling the IC engine, and that coolant can be some, that coolant can be either water or air or some other coolant. Okay. So mostly either we are using water or air. So here it is being asked that if you use air, then what are the disadvantages? So again, four options: high cost, bulky system, less efficient cooling, and option D, requirement of a water pump. Okay, so what are the disadvantage of using air as coolant? High cost, no. Bulky system, again, no. Mostly air cooling systems are for lighter applications. Less efficient cooling, yes. Requirement of a water pump, again, no. This is also not correct, right? Water pump will be required if you are using water as a coolant, right? And if you are using air as coolant, then you have various advantages. It is low cost, lightweight, you know, and but it is asking for disadvantages. Okay, so correct option should be option C, less efficient cooling. Okay, I hope this is clear. In lightweight and low cost applications, we are using air. For example, your motorcycle. So in motorcycle, you are not using water for cooling, right? You are using air. Okay, the engine is being cooled by air. And since it is less efficient, to make it more efficient, you are using fins. Okay, you know what are fins? Fins are just extended metal surface, so they increase the total surface area for the heat transfer. Okay, so in motorcycle, you can see the fins are there, right? So those engines are air cooled. Anyways, so we will move to the next question. Question number 3. What happens if a fuel with low self-ignition temperature or auto-ignition temperature is used in an SI engine, spark ignition engine or petrol engine? So, auto-ignition temperature. So it is the temperature. Uh, if the temperature of fuel is more than auto-ignition temperature, then fuel will auto-ignite, right? Without help of any external agent. For example, spark plug. Okay, so you don't need a spark plug. Fuel will auto-ignite it. So if a fuel has low self-ignition temperature and if it is used in an SI engine, then what will happen? Option A, engine will run more efficiently. Option B, the engine will experience knocking. Option C, engine will require more spark advance. Or option D, engine will have reduced emissions. So again, you can easily answer this question. And I hope that you must have, you know, marked option B as the correct option. Engine will experience more knocking or pinning, right? So, knocking, we have already discussed. I will quickly explain it again. So in an SI engine, what happens? Uh, During the intake stroke, the mixture of air and fuel comes inside the engine chamber, combustion chamber, and this is compressed in the compression stroke, and near the TDC spark plug will ignite the this mixture. Okay, then there will be a flame, right? So flame will be traveling towards unburned region. Okay, so it is traveling in the forward direction. Okay, so whatever mixture is behind this flame, that has already burnt. Okay, so this mixture has already burnt. So because of combustion of this mixture, the temperature and pressure inside this chamber will become quite high, and this part of mixture, this is unburnt, right? This is still unburnt because the flame front has not reached in this location. Okay, but sometimes what happens, if the temperature and pressures are so high, especially temperature is so high, so that this unburnt mixture gets auto ignited in very uncontrolled manner, in some very random manner. So that is called knocking, because it burns with some knocking sound. Okay, so that is knocking. Okay, so what we want, we don't want knocking, we want that this unburnt mixture should burn only after this flame front has reached there. Okay, so we want the controlled combustion. Okay, we want that this should burn because of this flame. Okay, when this flame reaches there, then this should burn. But if it gets auto ignited because of very high temperature, and it is random and uncontrolled, that is called knocking. Okay, so this knocking will occur how? Because of auto ignition. So if the auto ignition temperature of the fuel is less, then the tendency of fuel for getting auto ignited will be higher, right? So we don't want low self-ignition temperature. We want a higher self-ignition temperature, so that the tendency of knocking is reduced. Okay. So the fuels which have higher auto-ignition temperature, they this quality is usually quantified by something called octane number. Okay. So the fuels which have higher octane number, they will have higher self-ignition temperature, so that they will not get auto-ignited, and they will prevent the knocking in SI engine. Okay, so the fuels, good fuels for SI engine should have higher octane rating. Okay, and the good SI engine fuels and good SI engine fuels are usually bad CI engine fuels. Okay, so for this question, I hope that this is clear. Uh, that you should be able to answer this question, right? The engine will experience knocking and pinning if the fuel has low self-ignition temperature. Okay. So if there in doubt, then you can ask, or we can move ahead. Okay. Question number 4. How the ignition delay period in a CI engine can be reduced? So first of all, you should know what the ignition delay is, right? So in CI engine, what happens? We have discussed it many times that instead of fuel air mixture, we are getting only air during the intake stroke. Okay, and that air get compressed during the compression stroke, and that air gets very hot. Okay, the temperature is becomes very high, and in that high temperature air, the fuel is injected using some nozzle, and because of the higher temperature, that fuel get auto ignited. Okay, so what happens? This is, let us say, compressed air. Okay, this is your piston, and this is compressed air. Here you have compressed air. You have here you have compressed air. Okay, and this compressed air is very hot, right? And you inject the diesel in this hot air. Okay, you inject the diesel, so diesel will come out as a spray. So what happens? You start injecting. Okay, for example, you want to inject, let us say, some mass m of the diesel. Okay, so it will take some time, right, to complete the injection. Okay, so when you start the injection, the fuel will come out as spray, and after some time, the start of injection, this fuel will get start burning. Okay, so the burning is not immediately after the injection, start of injection. Okay, so there is some delay between start of injection and the start of combustion. Okay, so that delay, that time difference is called ignition delay. Okay, so ignition delay is basically, ignition delay is delay or time difference between start of injection and start of combustion. Okay. So that time period is called ignition delay. So this ignition delay depends on many, many parameters. Okay. So ignition delay. So this has this depends on mainly this depends on many parameters, and those parameters can be divided in two parts. Okay, one is called physical delay, and another is called chemical delay. So as the name suggests, that physical delay is associated with the physical changes, and chemical delay is related to chemical changes. So when it is injected, it comes out as ligament, and that those big ligaments are broken down. Okay, and they form bigger droplet, and those bigger droplet are again break down, so they form the smaller droplet, and those smaller droplets get evaporated, and after evaporation, or rather I should say during this whole process, the mixing is also taking place. Okay, so air fuel mixing is there. Okay, so once it is mixed properly, or up to a certain limit, so that it can form some ignitable mixture, then there will be a start of some chemical reactions. Okay, so chemical reactions will be started, some radicals will be formed. Okay, and after some time the heat will be released. Okay, and that heat release can be observed as the increase in temperature rise or the pressure rise. Okay, so there are two delays, right? One is related to physical changes, for example, droplet breakdown, then evaporation, then mixing, and there are some related to chemical reactions, for example, formation of certain radicals, and then you know high temperature heat release. Okay, so both of these delays combined form the total ignition delay. Okay, so after this ignition delays, after ignition delay, you can expect the heat release. Okay, anyways, so this ignition delay depends on many parameters as we discussed. For example, evaporation at higher temperature, evaporation will be higher. Okay, since evaporation will be higher at higher temperature, so critical delay will be reduced. Why? Because at higher temperature, better evaporation means better mixing. Okay, and certain chemical reactions also depend on the rate of certain chemical reactions also depend on the temperature. At higher temperature, most of the reactions occurs at higher speed. There are certain reactions which can uh, rate of certain chemical reactions are lower at higher temperature, but most of the reactions are you know accelerated at the higher temperature. Anyways, so most of the time, the temperature increasing the temperature will reduce the ignition delay. Okay, so now let us see all these options one by one. So question was asking how we can reduce the ignition delay. So for reducing the ignition delay, the main thing is to increase the temperature, right? So this is the fundamental thing. So option A, it says by decreasing the compression ratio. So what will happen if you decrease the compression ratio? Decreasing the compression ratio will decrease the temperature after the compression, right? Near the TDC. So since temperature will be reduced, so ignition delay will be increased. Okay, so option A is not the correct option, right? So increasing the compression ratio can reduce the ignition delay, not decreasing the compression ratio. And option B, by ensuring the temperature at the end of compression stroke is sufficiently higher than the fuel self ignition temperature. So yes, this is the correct option, right? Option B is correct, because if the temperature is significantly higher than auto ignition temperature, then ignition delay will be reduced. Why? Because both physical delay and the chemical delay will be reduced. Okay. Option C, by using a fuel with lower C10 number. So this is also not correct, right? Because C10 number basically quantifies how easily or how easily a fuel can be auto ignited at you know at desired time, right? And option D, by reducing the fuel injection pressure. So again, this is not correct, because what happens? Fuel injection pressure affect this physical delay part. Okay, so what happened? So what happens due to fuel injection pressure? If the fuel injection pressure is higher, these droplets that are formed, they are finer droplet. Okay. If the fuel injection pressure is lower, then these droplets will be quite bigger droplet. Okay. And the smaller droplets are easier for evaporation. Or in another way, you can think like, if there are more finer droplet, then total surface area available for evaporation will be more, right? So what I mean is, just consider two scenarios. You have a fixed quantity of fuel. Okay. So in first case, let us say you are having certain bigger droplets of that fuel. And in second case, you have many finer droplets of that same fuel. So surface area in the second case, when you have more finer droplets, in that case, surface area will be more. Okay. So evaporation will be better and the air fuel mixing will be better. Okay. So physical delay will be reduced, right? So this is how the fuel injection pressure affect the physical delay part. More the fuel injection pressure is, finer droplets are there and physical delay is reduced. Okay. So that this is the reason that most of the diesel engines that we have nowadays, in most of these diesel engines, fuel is injected at very high pressure, like 500 bar, 1000 bar. So you can think that this is a very high pressure. Okay. 500 bar and 1000 bar, these are very big numbers, right? In one bar there is 10 to the power 5 pascals. Okay. So the reason being that we want finer droplets. And one more thing is that if you are having bigger droplets, then what can happen? The droplet, sometimes it may happen that droplet is not evaporated completely. So there can be some part that is not evaporated and it is not mixed with the air, and there can be incomplete combustion, right? If you have very big droplet, so what can happen? Some part of that droplet can remain unevaporated, and that will not be mixed with the air, and there will be not be complete combustion. So that unburnt fuel will come out as soot or sometimes particulate matter. Okay. So higher fuel injection pressure also reduces this unburnt hydrocarbon or particulate matter. Okay. So I hope all these things are clear, but for the question, it is quite easy to answer. That correct option should be option B, right? To reduce the ignition delay, the temperature after the compression stroke should be sufficiently higher than the fuel self ignition temperature. Okay. And so if it's clear, then we will move to the next question. Question number 5, it says, what is the octane number of an heptane? So again, four options: 50, 100, 0, or 15. So what is the correct option? What is the octane number of an heptane? So when you see this N, so this basically means you have simple normal chain, right? Okay, this is N heptane, and just balance the remaining valency of carbon. No branching, right? So please answer this question. I hope you can easily answer this. Hello. You have studied how the octane number is, measured. How do you quantify the octane number? So you have a mixture of N-heptane and isooctane, right? And heptane and isooctane. So N-heptane has the octane number of 0. So 0, and isooctane has octane number 100. Okay. So you prepare a mixture of n-heptane and isooctane. N-heptane has octane number of 0 and isooctane has octane number of 100. And this mixture should be prepared in such a way that the mixture should have the similar knocking characteristic as your actual fuel, okay, your sample. Okay, for example, you have some sample and you want to measure the octane number of that fuel. So what you do, you prepare a mixture of these two compounds in such a way that the mixture should have similar knocking characteristic as compared to your sample. So the percentage of this isooctane in the mixture, in that mixture that has similar knocking characteristic, that percentage will be equal to octane number of your fuel. Okay, so the percentage of isooctane, okay, this is equal to octane number of your sample. Okay, so isooctane has 100 octane rating and n-heptane has 0. So octane number of n-heptane is what? 0, right? So I hope this is clear. If there is no doubt, then we can move to the next question. Okay. Question number 6. What does a larger cetane number indicate? Till now we have discussed about octane number. Now cetane number. So larger cetane number indicate what? Longer ignition delay or shorter ignition delay or higher energy content or lower viscosity. So as we discussed that higher octane number is good for SI engine and higher cetane number is good for CI engine, because cetane number indicate how easily a fuel can get auto ignited. Okay, so the fuel which have higher cetane number, that means it will have very you know larger the cetane number means shorter the ignition delay. Okay, ignition delay we have already discussed, right? A large cetane number means shorter ignition delay. Okay, and also you can note that good SI engine fuels are usually bad CI engine fuels and vice versa. Okay, for example, alcohols, ethanol, methanol, these have higher octane number and lower cetane number. So they are good fuel for SI engine and bad fuel for CI engine. Similarly, dimethyl ether, dimethyl ether or diethyl ether, these have higher cetane number. So they are good for CI engines and bad for SI engines. Okay. So cetane number basically means shorter ignition delay. Higher cetane number means shorter ignition delay. Okay. So next question. What are the reference fuels used to define the cetane number? So as we discussed, for octane number, we have some reference fuels. For octane number, we have what? Isooctane and N-heptane. So similarly, for cetane number, we also have certain reference fuels. So what are those reference fuels? Option A, N-heptane and isooctane. So no, this is for octane number. Option B, N-cetane and hexamethyl nonane. Option C, ethanol and methanol. And option D, methane and ethane. So you can easily answer this question that ethanol and methanol obviously are not correct options, right? Because they have very, very low cetane number. Just discussed in previous question. And heptane and isooctane are for octane rating. So correct option is option B, N-cetane and hexamethyl nonane. Okay. So cetane has again 100 cetane number and this nonane has 0. Okay. And again, you prepare a mixture of these two compounds in such a way that the ignition delay of this mixture and your fuel sample is same. Then percentage of cetane in that mixture. Okay. Like that it is calculated. Okay. Correct option is B. Question 8. What percentage of heat generated by burning fuel is transferred into work by the engine? So you know that heat generated by fuel, all of that heat is not converted into work. Okay, there are a lot of losses. Okay, a significant amount of that heat is gone, is lost because of exhaust, and a significant amount of that fuel is lost due to heat transfer losses, and certain part of that heat is lost due to parasitic load and due to friction. Okay, so a lot of losses are there, and whatever is remaining that appears as the work output. So it is asking that what percent of heat generated by burning fuel is transferred into work by the engine. This is not 100%. Only a small fraction is converted around, and that amount is approximately 1/3. Okay, the correct option 10 to 20. So no, this is wrong. This is too less. 70 to 80. Again, this is not correct. 30 to 40, it is correct. Okay, most of the cases it is the correct. But nowadays, what engineers and scientists are trying to do is they are trying to design engines such a way that you get efficiency, more efficiency, like 50%. Okay, sometimes even more than 50%. So there are various technologies. Okay, new technologies are coming, and that I hope they will help us providing better efficiency. Okay, but for the time being, we can select the option B as correct option. But in future, there will be engines, commercial engines available that will have 50% efficiency in the range of 50%. Okay. So this was the question number 8. Now let's move to question number 9. Question number 9 says, what are the main disadvantageous feature of using water as coolant? So we have discussed that engines are either water cooled or air cooled. Okay, or there can be some other coolant. But these coolants like water and air are easily available. So most of the time these are used as coolant. There can be certain, additives. In this question, it is asking that what are the disadvantages of using water as coolant. So option A, high cost and it promotes rusting. Option B, low specific heat and high viscosity. Option C, high boiling point and low freezing point. Option D, low density and high vapor pressure. Let us see all these options one by one. High cost and promotes rusting. So Yes, it is correct. It promotes rusting. And high cost. Well, you should use good water. Okay. So of course that will have higher cost, and there will be certain additional infrastructure as well, right? Pump and all. Low specific heat and high viscosity. So this is not correct, right? Water has higher specific heat, right? That's why you are using water. Option C, high boiling point and low freezing point. So again, this is not correct. If certain coolant has low freezing point and high boiling point, it is a good feature, right? Because at winters, when the temperatures are very low, specifically in very cold countries. So if the freezing point is very low, then it is better, right? Your coolant, your water will not be freezed, right? And high boiling point, this is also a good feature. Low density and high vapor pressure. So this is also not correct. Water have, reasonably good density. So the only correct option is option A. It promotes rusting. So your, cooling jackets or water jackets, rusting can be there. Okay. So maintenance will be required on time to time. Or what you can do, you can add some additives which can reduce the chances of rusting. Okay. So now let's move to question number 10. Says what additive is commonly mixed with water to use it as a coolant in colder climate. So as we discussed in previous question that in certain colder climate countries, sometimes temperature is dropped below the freezing point of water. So water that is coolant that can freeze, right? So what we do, we add certain additives. So it is asking what additive is that? Glycerin, ethylene glycol, alcohol, or salt. Well, if you dissolve some salt or sugar into the water, that of course that will decrease the freezing point and it will elevate the boiling point, but that is not used as additive in coolants. Okay, so correct option here is ethylene glycol. So if you add ethylene glycol to water as additive, so it will decrease the freezing point. Okay, so the chances of freezing of the water, so those chances will be reduced. Okay, and ethylene glycol will also reduce the tendency of rusting, and this ethylene glycol can also work as lubricant for your water pump. Okay, so this addition of ethylene glycol will this provides various advantages. Okay, so it is used as additive in the coolant. Okay, so what are those advantages? It increases, sorry, it decreases the freezing point. Decreases the freezing point. It prevents rusting, and it can also provides lubrication or pump, right? Okay, clear. Now can we move to the next question? Question number 11. Question number 11 says, which of the following is an advantage of air-cooled engines compared to water-cooled engines? So again, we have discussed this in some previous question. Option A, more efficient cooling. Option B, lightweight. Option C, quiet operation. Option D, better temperature control. So the correct option is lightweight. Okay. So when your requirement is to have lightweight engine, then you don't use then you don't use water cooling. Okay, because water cooling is bulkier. Okay, and it increases the weight. So in your bikes, your motorcycle, your engines are air cooled, right? And more efficient cooling, no. Water cooled engines are more cooling is better. Okay. Option B, question number 12. What is the purpose of a cooling water jacket in an engine, in an internal combustion engine? So again, this is quite easy question. Purpose of cooling water jacket is to provide passage, right? To provide a way, uh, a circulation around your cylinder. Okay, for the cooling purpose. So there are water jackets around the cylinders. Okay, in the case, and also in the head. Okay, in the engine head. Okay, so water flows through those water jackets for cooling purpose. Okay, so these water jackets are basically passage for water to flow, water or coolant flow. And what is the purpose of cooling? Four options are there. To increase the temperature of engine, no. You don't want to increase the purpose of coolant is not to increase the temperature. Option B, to reduce the temperature of engine and prevent damage to its components. So yes, it is correct option, right? Instead of reduce, basically we should say to control the temperature of engine, right? Control the temperature of engine and prevent damage to its component. Option C says to increase the pressure inside the cylinder. Well, cooling will not increase the pressure, right? To reduce exhaust emissions. Again, this is not the correct option. Only correct option, the most accurate option is B. Okay. Now we will move to question number 13. Turbocharger engines are those in which charge density is increased by. So I think turbocharging or the boosting has not been discussed. So I will quickly discuss the boosting. Okay. So we have discussed that in both in CI engine and in SI engine, what is called volumetric efficiency. So for example, in CI engine, let us say, what happens? This is your intake port. During the suction stroke, the air comes in, right? Why? Because the piston is going down. So here in the cylinder region, the low pressure will be created, right? Some vacuum type of pressure will be reduced, and outside pressure is equal to 1 atmospheric pressure, right? So because since the pressure inside the cylinder is lower than the atmospheric pressure, so air will come inside. Okay, and when the piston will reach the bottom dead center, the whole chamber will be filled with the air. Okay, then this air will be compressed. Okay, so what happens if there is sufficiently time available for filling this cylinder, then pressure inside this cylinder will be equal to what 1 atmosphere pressure. But in the real case, the pressure will be little lower than the atmospheric pressure. Okay, because volumetric efficiency cannot be more than 100%, right? For the naturally aspirated engines. Okay, and you also know that for higher load, you need to burn more air fuel mixture, right? If you need more torque at higher load, what you do? You burn more fuel. But the quantity of fuel that you are burning, that is limited by the amount of air. Okay, if you want to burn more fuel, then you also require more air, right? But in naturally aspirated engines, the amount of air that you are filling inside the cylinder, that is limited uh, by the size of your cylinder, right? For example, if you have 1 liter cylinder, then even at 1 atmosphere pressure, the amount of air that you can fill inside 1 liter cylinder, that will be limited, right? At let us say at 1 atmosphere pressure, how much air you can fill inside 1 liter? You can easily calculate, right? Using ideal gas equation. But at higher load, since you want to burn more fuel, then you need more air, right? So how to get more air? One thing is clear that if you are sending air at 1 atmosphere pressure, the amount of air you cannot increase. So what you do, you send air at higher pressure, or you can say you are sending air, compressed air. Okay, you are sending air at higher density. So instead of sending this, air directly from the atmosphere, what you do, you compress the air. Okay, so there will be some compressor. Okay, and you will be sending the compressed air. Okay, compressed air. So now using the same cylinder of the same size, you can get more air. And since now you have more air, you can burn more fuel. And the same engine which was producing, let us say 40 kilonewton, 40 Newton meter, the same engine can produce higher torque. Okay. So the power of the engine will be increased, right? So your 10 kilowatt engine that can produce, 15 kilowatt. Okay. What are you doing? You are just sending the compressed air. So what you need? You need one compressor. You need one compressor. And you know that compressor is work consuming device from thermodynamics, To run the compressor, you need some work. Okay. Now, this work for running the compressor, that you can get from the engine shaft, right? From your shaft, you can connect this compressor. Okay. And you can get the compressed air. But what will happen? This compressor will be extracting some part of power output from your engine, right? So it is like a parasite, right? So whatever power you are producing, some part of that power will be going to run the compressor. So you don't want to waste your work. So what you can do is, instead of extracting power from the shaft, you can use a turbine. Okay, so you can use a turbine. You can use a turbine, and this turbine will be run using the exhaust gas. Okay, so exhaust gas which are coming out from your engine, that have significant enthalpy, right? So that enthalpy, instead of throwing that into the environment, just wasting that, you can use that enthalpy of that exhaust gas to run a turbine. Okay, so you can run a turbine using the exhaust gases. Okay, and this turbine, whatever energy you'll be getting from the turbine, used to run this compressor. Okay, so you can connect this turbine and compressor. Okay, So this whole procedure is called turbocharging. Okay, this is called turbocharging. So what are you doing in turbocharging? You are utilizing the enthalpy of exhaust gases to run a turbine, and that turbine runs a compressor, and that compressor compresses the air, and that compressed air is sent into the cylinder, engine cylinder. Okay, so since the air is compressed, it has higher density. Okay, and since you have more air, you can burn more fuel and you can get more power. Okay, now there are many other things to understand. For example, when you compress the air, then during the compression it becomes very hot, right? And at higher temperatures the density of air is reduced. Okay, so instead of sending this compressed air directly to engine, sometimes what you do, you also use an intercooler. Okay, you also use an intercooler. Okay, so why you use intercooler? So that you can cool down this compressed air. Okay, so again, if you send directly, then it is without intercooler, right? And sometimes you do cool this compressed air, then the density is more. Okay, so this is called turbocharging. There is one more something called supercharging. It is also similar. The difference is that instead of getting the power from turbine, instead of running a turbine, what you can do, as I explained earlier, you can get the power from the shaft itself and you can run the compressor. But in that case, your total power output will be reduced a little bit because you are using certain amount of power to run the compressor. Okay, so both of these have certain advantages and disadvantages. For example, the turbocharger which is run by the exhaust gases, that will have some delay, right? Turbo lag, we call that turbo lag. Why? Because it is connected with the turbine and turbine is run using the exhaust gases. Okay, so this whole loop, okay, so whatever power changes or sorry, whatever the load changes are there, so it will take some time to some time for whole system to adjust according to the changed load, right? For example, if the load is reduced, then the enthalpy of exhaust gases will be reduced, then turbine whatever power the turbine was producing or the rpm, that will be reduced. Okay, then compressor, the air flow rate of compressor, that will also be reduced, but whole thing will take a little bit of time to get adjusted to the new to get uh, adjusted to the new conditions. Okay, so that is called turbo lag. In supercharging, there is no turbo lag. Okay, but supercharger, but in supercharging you extract the power from a shaft, so it is like a parasitic load. Okay, but anyways, so this both of these are boosting techniques to increase the volumetric efficiency. Okay, to burn the mole fuel at the same for the same engine size. Okay, so the same engine which was producing some power earlier, same engine will produce more power. Okay, so I hope the background is clear. Now let us move to the question. The question was saying turbocharging engines are those in which charge density is increased by option A, separate air compressor. So yes, air compressor is there. Option B, compressors driven by exhaust gas turbine. And option C, cooling the inlet air. None of the above. So the most accurate option should be option B. Okay, but other options you can also tell that cooling the inlet air, you are not basically you are not only cooling simple air, you are not cooling the simple air, but you are cooling the compressed air. Okay, so if the option C was like cooling the compressed air, then it could have been the correct option in case of the intercooler. Okay, but sometimes you don't use intercooler. Okay, the most accurate option is option B, compressors driven by the exhaust gas turbine. Okay, so I hope this intercoolers, sorry, this turbocharging is clear. Okay, how this work, what is the purpose, okay, what are the various components. And if there is no doubt, then we can move to the next question. Question number 14. A turbocharged four-stroke direct injection diesel engine has a displacement volume of 0.0259 meter cube or 25.9 liters. The engine has an output of 950 kilowatt at 2200 rpm. The mean effective pressure in megapascal is closest to. So these type of questions we have solved many times in previous sessions. So you can solve it easily. So we have displacement volume, we have power output, and we have engine speed. And we have to calculate the mean effective pressure. We have studied what the mean effective pressure is. What is the mean effective pressure? Mean effective pressure is defined as work output per cycle, है ना? Work output per cycle divided by displacement volume. So displacement volume is given. We need to calculate the work output per cycle. Then we will be able to find the mean effective pressure. Okay. So power output is given. How much power output is given? 950 kilowatt. Right. So this means 950 into 10 to the power 3 joules per second. Right. And engine speed is given 2200 revolutions per minute. So this means 2200 divided by 2 cycles per minute, right? Cycles per minute. We have discussed in some previous session that in four-stroke engine, for completing one thermodynamic cycle, we need 2 revolutions, right? And in two-stroke engines, one cycle is completed in 1 revolution. Okay. So since it is a four-stroke engine, okay. So for completing one cycle, there should be 2 revolutions. Okay. So if there are 2200 revolutions in 1 minute, so there will be 2200 divided by 2 cycles per minute. Okay. And there will be 2200 divided by 2 divided by 60 cycles per second, right? Per second, right? So in 1 second, there are these many cycles and this much energy is produced, right? So you can say that 950 into 10 to the power 3 joule is produced in 2200 divided by 2 into 60 cycles, right? So you can calculate work output of one cycle. So this will be 950 into 10 to the power 3 divided by 2200 divided by 2 into 60 joule, right? So now we need to calculate this value. Nine hundred fifty into 10 to the power 3, 1, 2, 3 divided by 60. So this comes out to be 40.39 joules. Okay. And displacement volume is given 0.259. So mean effective pressure, this should be equal to 14.39 divided by 0.0259 Pascal. So we have made some mistake. So that mistake should be there because this is very less amount. Okay. So our output is given 950 kilowatt. Sorry. So correct value should be 5 into 1.8 into 10 to the power 4 joule. Okay. 5.18 into 10 to the power 4 divided by 0.0259 pascals. This should be the mean effective pressure. Okay, 5.18 into 10, 5.18 into 10 to the power 4 divided by 0.0259. Okay, so it is coming out to be 2 to the power 6 Pascal. Sorry, 2 into 10 to the power 6 Pascal. Or you can say it is 2 megapascal. So this is mean effective pressure. Okay. So the correct answer is 2 megapascal. So is there any option? So option B. Okay. So is there any doubt? Hello?
No doubt, sir.
Okay. So should we move to next question? Okay. Question number 15. So in cylinder pressure data for a engine is given. Okay. So actually I wanted to show you uh, some, real data from a real experiment. So I have a Excel file. Okay. So in cylinder pressure data is given in the Excel file. So here you can see that screenshot of that Excel file, and specification of the engine are given, compression ratio, bore, stroke, speed, fuel consumption rate, all these things are given, and you have certain data. Okay, so this data you can see, and based on this data we have to do certain calculations. We have to draw the PV curve, and we have to calculate these brake mean effective pressure, indicated mean effective pressure, thermal efficiency, brake thermal efficiency, mechanical efficiency, and all these things. Okay, so the data we have is crank angle degree and pressure at 20% load. You can just ignore this 20%. Okay, so in one column we have crank angle degree, and in second column we have pressure. Okay, so how this data is measured, I will quickly give you a brief overview. For example, let us say you have a engine. Okay, you have one engine. So there is a pressure transducer. Okay, here there can be injector, and there will be some pressure transducer. Okay, pressure transducer, and this pressure transducer, this will measure the pressure inside the cylinder. Okay, and there will be some electronics. Okay, data acquisition system. Okay, and there will be an angle encoder. Okay, angle encoder will be there. So both of this data using the deck will be measured. Okay, so here let us say you have your computer. Okay, so you have pressure versus theta values. Okay, so here you can see it is recorded at a resolution of 0.5 degree, right? This is the resolution of this measurement of this experiment, right? So at 360 degree, then 359.5, then 359, then 358. Okay, so like this data is measured. Okay, so what you will get, you will get CAD versus pressure data. Okay, are you getting? Then using this CAD versus pressure data, you can get pressure volume data. Okay, you can convert this crank angle degrees into volume. Can you convert this? You know what this crank angle degree is, right? So crank angle degree basically tells how much, tells the rotation of crankshaft. Okay, so 0 degree or 360 degree, this is corresponding to TDC. Okay, this is TDC, and this is your CAD. Okay, theta. So using this theta, can you tell the volume, cylinder volume? Hello? Let's say this is your cylinder. Okay. Piston. Okay. This is your connecting rod. Okay. And this is your connected to crankshaft. Okay. So it is rotating. So when it is going in this direction, it will move, it will be going in the upward direction. Okay. This angle is theta. This angle is theta, and this is your volume. Okay. So let us say the length of connecting rod is L and stroke is A. Then can you tell the volume? Hello? We have the bore. Okay. So bore is basically diameter. We have the bore. Okay. We have the stroke. What we have? Just let me note it down. We have bore. We have stroke, and we should also have the length of connecting rod. And we should have compression ratio. So can you tell the volume of the cylinder? It is quite easy, right? You what do you need? You need this area and you need this height, right? This height. You know the volume of cylinder. It is pi r square multiplied by h. Correct? Is there in doubt?
No, sir.
Okay, so you can easily tell the volume, right? Okay, so let us try to write the expression for volume. So volume, as we discussed, is, let me make this diagram again. This is cylinder, a piston. Connecting rod. This is your crankshaft. This angle is theta. Okay. So what will be the stroke? You know what is stroke? So stroke is uh, distance between TDC and BDC, right? Correct? Right?
Yes, sir.
So if the radius of crankshaft is A, if the radius of crankshaft is A and the length of connecting rod is, let us say, L. Okay, so if the length of or the radius, crank radius is, if the crank radius is A, then what will be the stroke? Hello. Well, this is quite easy. Okay, so you please answer. Sorry. If the crank radius is A, then what should be the stroke length? Okay, let me give you some hint. Uh, what will happen at TDC? Piston will be somewhere here. Okay, let us say piston is somewhere here, and crank, sorry, this connecting rod will be completely straight, and the angle will be 0. Okay, so this is your, crank, and this is your connecting rod. Okay, so this is at TDC. Okay, and what will happen at BTDC? Let us say this is your BTDC, and sorry, this is your BDC, bottom dead center, and this will, after 180-degree rotation, it will come here. Okay, so are you getting what I'm trying to explain? So this, okay, let me little draw it little skewed. Okay, so somewhere near TDC, if this is your, let us say, crank, and it will be your connecting rod. Okay, right? So this is near TDC. Okay, this is near TDC. Green one is near TDC. So once this angle will become 0, okay, this thing will become 0. This angle will become 0, this angle. Okay, then this will be completely straight. Okay, this connecting rod and crank will be completely straight. Okay, and near bottom dead center, what will happen? Let us say this is your piston at near bottom dead center, and this is your crank, and it will be something like this. Okay, again, at exact bottom dead center, they will overlap. Okay, connecting rod and crank. So now I hope you should be able to answer. If the crank radius is A, then what should be the stroke? A stroke is basically distance between top dead center and bottom dead center. Hello. If this is clear what I explained, then you can easily answer, I think. So please answer. What should be the stroke in terms of the crank radius? So any of you can answer. Senthil Kumar or Sayed, please. I want you to drive this expression of volume in terms of crank angle degree. Then we will do the calculations with the data and try to calculate whatever is asked.
So little bit I'm confusion, sir. Please try to explain, sir.
Okay, it is clear what I explained till now. When this green one is basically near the TDC, and this what color is this? This pink color. Okay, so this is near the bottom dead center. Okay, so what is this difference? What is this difference? This would be 2A, right? Correct.
Okay, sir.
So the difference between top dead center and bottom dead center, this would be 2A, correct? Isn't it? Are you able
Yes,
to
sir.
visualize? Are you able to visualize the mechanism that is working here?
Yes, sir. Yes, sir.
This crank is rotating, okay, and because of the rotation of this crank, this piston is moving up and down. So when this crank is at 0 degree, okay, when it is overlapping with the vertical, and it is in the upward direction, then the piston will be at TDC. And when it is again vertical, but it is at the bottom side, then the piston will be at BTDC. So this difference, this should be equal to 2A, and this should be your stroke, right? So stroke is basically difference between TDC and BTDC. Sorry, bottom dead center, right? So this is stroke. So stroke is basically 2A. So stroke is given in the question, and crank radius will be half of that. Okay. And what we need, let me add another page. This is some imaginary line. I'm sorry, it is not very symmetric. Let me try again. Okay, this angle is theta, this is A, and the length of connecting rod is L. So you can calculate this distance, right? Let us say this is S. So edge is basically distance between piston. Edge is distance between piston and crank center. Okay. So using trigonometry, you can tell what will be the S, right? You can easily calculate that. Correct. So how will we calculate S? For calculating S, let us draw a perpendicular from this point to this green line, this vertical line. Okay. So let us say this is O, and let us say this is P, and this is, let us say, M. This is, let us say, N. Okay. So just focus on this right angle triangle. So in this triangle, in triangle M N O, the MN, the length of MN will be equal to A sin theta, right? And since this is a right angle triangle, you can use Pythagoras theorem. So you can write, instead of writing in terms of this, you can simply write it as A cos theta. मतलब MO is equal to A cos theta, right? MO is equal to A cos theta. And if you see another triangle, this triangle, in triangle PMN. You need PM, right? You need PM because S will be equal to MO plus PM, right? Correct? So
Yes, sir.
MO you already have, it is A cos theta. Now you need PM. So MN will be A sin theta. And since it is a right angle triangle, you can use Pythagoras theorem. So PM will be under root L square minus MN square, right? Correct? So PM will be L square minus A square sin square theta. Correct? This is PM. So your S will be equal to MO, that is A cos theta, plus under root L square minus A square sin square theta. Okay? This is simple trigonometry, right? Correct?
Yes, sir.
Okay. When the piston is at top dead center, theta will be equal to 0 or 360, right? So S will be equal to A plus L, right? At bottom dead center, S will be equal to L minus A, right? Let me draw this diagram again. This is, let us say, top dead center, and this is bottom dead center. So when the piston is at top dead center, there will be some clearance. Okay, let us say this is some clearance. Let us say this is C. Okay. So clearance volume will be pi r square. R is bore. Okay. R is bore radius. Pi r square into C. This is clearance. Okay. And when piston is at bottom, this is at TDC. है ना? At bottom dead center, volume will be pi r square into C plus 2a, right? This distance will be added, correct? And you know, compression ratio. This is defined as the maximum volume to the minimum volume, or volume at bottom dead center divided by volume at top dead center. Okay. So compression ratio is equal to volume at bottom dead center, that is pi r square C plus 2a divided by volume at top dead center, that is pi r square times C. Okay. So this pi r square will cancel out each other. So compression ratio in terms of these geometrical parameters, you can write it as C plus, sorry, 1 plus 2a by C. So from here, because you have compression ratio, it is given in the question. Okay. Stroke is given in the question. You can find the C. Okay. So what is given in the question? Compression ratio is given 17.5. Stroke is 106. Sorry, 116. So this is actually 2a. Okay, so from here you can find the C, right? So 17.5 is equal to 1 plus 2a. A was how much? Sorry, 2a was 116 divided by C. So you can find the C, right? So C will be equal to 16.5, actually 116 divided by 16.5. Okay, right? Now you can write the volume of cylinder at any crank angle degree. So at any crank angle degree, you can write the volume. You just need this H, okay, at any uh, crank angle. You have this S, you need only H, okay? Is that clear? Till now, everything is clear? Hello?
Yes, sir.
So now you can write the volume in terms of these parameters, right? You have all these parameters. So volume will be clearance volume plus pi r square plus L plus A minus S. So from where it comes, just try to understand. This is your top dead center. Okay, this blue one is your top dead center. And at any crank angle degree, S is the distance between the piston and this center. Okay, and this distance, the distance of TDC from the crank center, it is L plus A, right? So this distance will be how much? This distance will be how much? This will be L plus A minus S. Is that clear? This one. Hello? Is it clear?
Okay, sir.
Because the distance from TDC to this center of crank, it is L plus A, and at any theta, the distance of piston from the center is given by S, that formula that we have derived. So the distance from this TDC to the piston position at any theta, that will be L plus A minus S. Okay. So this distance is L plus A minus S, and distance from this distance of this fire deck to the TDC was C, that we have just derived. Okay. Or you can see that this upper part is clearance volume. This is clearance volume. And this is some swept volume, not the total swept volume, the swept volume at any particular CAD. Okay. So angle, so the total volume at this CAD will be the clearance volume plus this additional volume. So what will be this additional volume? This additional volume will be pi r square times this distance. So what is this distance? This distance is L plus A minus S, and S we have already derived. Where is S? Okay, sorry. This we have already derived, right? So this will be equal to VC plus pi r square times L plus A minus A cos theta minus under root L square minus A square sin square theta, right? And this part is minus S. Okay. So in the data, you have crank angle degree theta. In question, stroke is given, so you have A, right? Clearance volume, we just calculated from the compression ratio. What else we need? We need length of the connecting rod. So let us check given in the question. Well, length of the connecting rod is not given. Okay, length of the connecting rod is not given. So let me write the length of connecting rod. We need to take some value. Okay, ideally it should be given in the question, but it is not complete, I think. So for small and medium sized engines, the ratio of connecting rod to this radius, it is usually in the range, this is in the range 3 to 3.5. Okay, so this is a design parameter. Okay, so in most of the engine, the ratio of connecting rod to the crank radius, it is approximately 3 to 3.5. So since this question in this question it is not given, so we will assume. Okay, so let us assume this ratio is, let us say some any value between 3 to 3, let us say 3.2. Okay, so we can take L is equal to 3.2 into A. Okay, we will take this value and proceed with the same value. Okay, so from this we will get L is equal to 116 by 2 into 3.2. So it will come out to be 185.6 mm. Okay, so now we have L. So let me complete the question. Okay, so question में इसको लिख देते हैं. Assume L by A is equal to 3.2. Okay, now we have L. So now we have everything to convert the theta into volume, right? So the data that we have in Excel sheet in pressure and CAD, that we can convert into PV data, right? And from PV diagram we can calculate indicated things. So why I am calling indicative thermal efficiency or indicative mean effective pressure, that we have already discussed. You know why, what the significance of this term? Actually, in the olden days, there was a device called indicator. So that indicator used to plot the PV diagram. Okay. So there was some arrangement. I have shown that diagram in the previous session. If you go, you know, go through that session, you will get that diagram. Okay. So that that indicator was a device that used to draw the PV diagram. Okay, so whatever information you were getting from that PV diagram, so all that information were called indicative parameters. Okay, indicative break thermal efficiency or indicative mean effective pressure. Okay, but nowadays we don't use that diagram, that that device anymore, because now we have better, now we have more accurate sensor, we have pressure transducer. So nowadays we are getting this type of data. Okay, so here is that data. This is CAD and this is pressure. Okay, now we need to convert this CAD into volume. So this is, so are you comfortable with Excel or you use some programming language? Because see, there are a lot of data points, right? We have more than, we have more than 40 and 1400 data points. Okay, so either you can use some programming language or you can just use the Excel. So what do you prefer? You prefer Excel or now it is hanged off? You prefer some language, programming language, or Excel itself? Okay, let us proceed with the Excel. तो क्या फार्मूला था? So volume will be, so volume will be clearance volume. Clearance volume just given or not given? Well, bore is given, a stroke is given, and compression ratio is given. So you can calculate the clearance volume. So let us quickly calculate the clearance volume. So we have swept volume. What will be swept volume? Swept volume will be pi r square into stroke, right? So it will be pi 102 divided by 4 square into 116 by 2. Okay, so this is the swept volume, and I am getting this value to be 947.87 centimeter cube. You just convert all these values in centimeters. This was in mm. Now I am getting this in centimeter cube. Okay, so clearance volume, sorry, swept volume plus clearance volume divided by clearance volume, that is compression ratio, and that is 17.5. So from here we should get compression ratio is equal to 57.3 39 centimeter cube. I'm not doing the full calculation, all the steps. I have already these values, so I'm writing it directly. You just cross check if you are getting the same values. Okay. So this is the VC 57.39. So 57.39 plus pi square by, sorry, pi d square by 4. Okay, d is bore diameter, plus this we have just got L. This is 18.57 plus A is 5.8. Okay, I'm writing everything is in centimeters. Okay, minus 5.8 cos theta minus under root 18.56 L square minus 5.8 square sine square theta. Okay, I have just substituted the values. The values were in mm and I have converted all these values in centimeters. Okay, so if you simplify this, you will get V is equal to 204. It is just simplification. Okay, you can use your calculator or verify these values. 81.7128 times 5.8 cos theta plus under root 344.4736 minus 33.64 sine square theta. Okay, so this will be the volume. So for you just need to substitute these theta values. Okay, and you will get the volume. So for volume, you can write this formula. In fact, I have already written this. Okay, this I have written. Can you see? I have simply wrote down the same thing, formula for volume. Okay, and you get the volume values for all corresponding theta. Okay, so you have volume in cc. So you have volume in cc. Now you have pressure, right? You have pressure and volume. Okay, so you can draw the PV curve and P theta curve, all type of curves. So maybe in tablet it is not possible, so I will to use the laptop. Just give me 1 second. Okay, this is P theta diagram. This is P theta diagram. The pressure and y-axis is pressure and x-axis is tank angle degrees or theta. Okay. Similarly, you can draw PV curve. PV curve. So let me draw PV curve. This is PV curve. This is just reversed. On x-axis, this I plotted pressure. Okay, let me just change the axis. Maybe I should share the screen of my laptop. Just give me 1 second. Mhm. Screen is visible? Not visible, I think. Screen visible?
Yes, sir.
Okay. So on y-axis that plotted volume. So let me change it. So that's why it is better to use some programming language. Again, same problem. Great. Okay. So this is a PV diagram. Can you see this diagram?
Yes,
Hello?
sir. Yes,
Okay,
sir.
so this is a typical PV diagram for a SI engine. Sorry, IC engine. Okay. And
Okay, sir.
compression ratio is 17.5. So can you tell me which type of engine this can be? A compression ignition engine or spark ignition engine?
Diesel engine, sir.
कौन सा?
Diesel engine.
Diesel engine. Yes, compression ratio is quite high. Okay, so this is a typical PV curve for a typical diesel engine. Okay, so this type of curve, I think you have already seen, right? So this is from the actual data. Okay, so if you have PV diagram, then can you calculate the work done per cycle? This is correct.
Yes, sir.
Okay. Now you have discrete data, and for integration of discrete data, there are various techniques, numerical techniques. Okay, for example, let us say you have this curve. Okay, you have this curve, and you want to integrate this curve. So integration means area under this curve, correct? So let us say you want to integrate from point A to point B. So integration means you want to calculate this area, right? Correct? Is that clear?
Yes, sir.
So what can you do is you can uh, divide this whole thing into many strips. Okay, so what let us say here, this is PA, and here it is PI, here it is P, here it is, let us say P1, P1, P2, P3, and so on. One, okay, so here let us say it is better use this one. You want to integrate this curve from A to B, you can take a strip. Okay, let us say this is P1, at here it is P2, here it is V1, here it is V2. So what will be the area of this strip? So if you zoom in this strip, and then you can probably make n trapezoidal. Okay, can you see this trapezoidal? If you join the point P1 and P2, so if this trapezoidal is very thin, okay, so that the V1 and V2 they are not very far apart, then the area of this small strip will be approximately equal to the area of this trapezoidal, right? Right. So area of this trapezoidal will be equal to, this will be, what is the formula of area of trapezoidal? It is the it is P1 plus P2 divided by 2 times V2 minus V1, right? Is this clear? This one? Hello?
Okay, sir.
Okay. So this is the area of one strip. So you can divide the whole, area under this curve in many strips like these. Okay, and you can add the area of all those strips. So this is for a continuous curve, but in our case we have discrete data. So discrete data means we have instead of curve we have many points, P1, P2, P3, like that we have. Okay, so what we can do is we can join these using these type of lines. Okay, our resolution is quite good. Okay, we are having 0.5 CAD. Okay, this is the resolution. Okay, this is, let us say, V1, V2, P1, P2, P3, like that. Okay, so what we can do is we can just take any at any strip, you just do this Pi plus Pi plus 1 by 2. Okay, you take any two conjugative pressure values and you take the average of those pressure values, and you take the width of this strip V2 minus V1, like that you will get the area of this trapezoidal, and you sum of you get and then you do the summation of all these areas of small trapezoidal, then you will get the total area under this curve. Okay, so this method is called trapezoidal rule. Okay, so similar rule you can apply here. So same rule you can apply here, then you will get the area under small strips. Okay, so you can see we are getting PdV. So how this PdV is defined, you can see, you just add B3 plus B4. So B3 plus B4 means two conjugative pressure values divided by 2. So that is average multiplied by D4 minus D3. So D4 minus D3 is the width of that strip. Okay. So in this manner, you get the area of one particular strip. So PdV is basically area under that particular strip, right? And summation of the PdV over the whole cycle will give this total area under this curve, and total area under this curve is basically work output of one cycle, right? Then you do the summation. Okay, the summation, can you see at the right corner, the summation, it is showing 6683. Can you see it? So here you can see the summation we have 6683. So pressure was in bar, this was in bar, and volume was in centimeter cube. So if you convert all these things in SI unit, so you'll have to multiply by 10 to the power 5 to convert bar into Pascal, and multiplied by 10 to the power minus 6 to convert cc cube into meter cube. So overall you will get 10 to the power minus 1. Okay, so just multiply this 6683 into 10 to the power minus 1 joule per cycle. Okay, this is the work done of one cycle. So you have 668.3 joule per cycle. Okay, so from PV diagram you have work done in one cycle. Okay, now you have work done in one cycle. Now you have engine speed. So from engine speed you can calculate how many cycles are there in 1 minute, and you have fuel consumption rate. It is given 25.17 milligram per minute. I think there is some mistake. Either this should be gram per minute or it should be 25.17 milligram per cycle. Okay, this should be either, okay, either this thing should be gram per minute or milligram per cycle. You need, because this is a quite big quite small value. 1 मिनट में अगर 25 मिलीग्राम डीजल जा रहा है तो बहुत कम है. Okay, so there's some correction. Okay, so either you take it as 25.17 gram per minute and proceed for your calculations, or you take it as 25.17 milligram per cycle, then you proceed for the calculation. You will also require the calorific value of the fuel, and you can assume that fuel is diesel. Okay, and then you can proceed for the calculations. Okay, so these are two more assumptions. Okay, based on these assumptions you can proceed for the further calculations. But now you have work done per cycle, you have engine speed. So from engine speed you can get how many cycles are there in 1 second, and since you have fuel consumption rate, so you know how much fuel is being consumed in 1 second, and you can take some value of calorific values. Then you will have how much heat you are getting from combustion in one cycle. Okay, since you have heat of combustion of fuel in one cycle and you are getting work output in one cycle, then you can get the indicative efficiency. Okay, and for brake thermal efficiency or brake indicator, brake thermal efficiency or brake mean effective pressure, you also need data from the brake or dynamo. Okay, so that data is also not given. That you can assume the torque at dynamo, like some value, let us take 40 Newton meter. Okay, this value can assume, and calorific value you can take it as, let us say, 45.5 megajoule per kg. Okay, so these are few more assumptions, but I think we are running out of time. We can solve this question in next session, but I hope that this is clear what we are trying to do. Okay, so this is how we get the data from experiments and how we analyze. Okay, the more important thing is this mechanism. Okay, this formula, how to drive, that should be clear. Okay, so we will stop here. You can take the screenshot or note down these values, and you can try to solve the problem yourself, and of course I will solve it in the next session. Okay,
Okay,
so
sir. Thank you.
okay, thank you.